Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous lecture we were discussing about frequency analysis, that is finding out the magnitude of an event having certain return period. On the context of frequency analysis, we have discussed about return period and the relationship between the return period and the exceedance probability. When we were talking about the return period is the average time period or the average recurrence interval for an event having a certain magnitude to get equaled or exceeded. In common man's language, it is the average time interval between the occurrence of an event having certain magnitude or having a magnitude greater than that, and the corresponding probability is represented by means of exceedance probability, and that relationship we have seen yesterday. So, in today's lecture we are going to discuss about extreme value analysis. So, let us move on to today's lecture on extreme value analysis. For carrying out extreme value analysis, we need to have understanding about extreme value distribution. Consider a series of data representing maybe annual rainfall or maybe annual maximum stream flow data. So, this data for long period can be divided into sub data series. For example, if you are talking about normal rainfall, we will be dividing the data series into a sub series having 30 years data points. In the similar way, for the analysis point of view, depending on the length of the data, we can divide it into sub series. Each and every subseries will be containing maximum value and also minimum value. So, these maximum and minimum values are representing the extremes. In the case of stream flow, the maximum values are representing the corresponding to the flooding value, and the minimum values related to stream flow or rainfall is representing leading to the drought. When we are carrying out the analysis, these values will be falling on the tails of the distribution which we are fitting. So, for the analysis of such variables, we need to have understanding about extreme value analysis. Extreme values are selected as the maximum or minimum value of sets of data. From the data, we will be selecting the maximum or minimum. We will be fixing a threshold value. Above that, what are coming, those are considered as maximum value, and lower range also will be fixing. Below that, the certain values are coming, those are considered as the minimum value. Both maximum and minimum values are considered as extremes. Extreme events lie in the extreme tail of the probability distribution of all observations, because extreme events have high magnitude and lower frequency. We know already that high magnitude events will be having lower frequency, less frequent those events will be occurring. Very high intensity rainfall, that is not a frequent event, that may be occurring after certain period of years. For those type of events, certain return periods will be there. That is the reason these extreme events will be lying on the extreme tail of the probability distribution of all observations. Example we know already, that is annual maximum discharge, annual maximum precipitation values. So, all these when we deal with analysis point of view, we will be making use of extreme value analysis, because for the construction of a water resources project or the design life of a water resources project, all these are depending on the extremes and the magnitude of the extreme events corresponding to certain return periods. So, we need to have the understanding about this topic. So, let us see what are the different approaches for carrying out extreme value analysis. There are commonly three extreme value distributions: extreme value type 1 Gumbel distribution, extreme value type 2 Fresher distribution, and extreme value type 3 Weibull distribution. So, these are the three extreme value distributions which we commonly use in hydrology. When it comes to maximum value, we make use of extreme value type 1 distribution. If it is related to droughts, we will be moving on to extreme value type 2 distribution. That way, depending on the random variable which we are considering, based on the analysis will be different. So, here in this lecture, I am going to discuss about extreme value type 1 analysis. Why this distribution is called Gumbel distribution? This type 1 extreme value type 1 distribution is used by, for so many analysis, Gumbel has used this particular method of extreme value analysis, and especially for flood frequency analysis, Gumbel utilized this technique. That is the reason why this extreme value type 1 distribution is also known as Gumbel's distribution. When the analysis is related to flooding, that is maximum value, then we will be making use of extreme value type 1 distribution, that is the Gumbel distribution. The probability density function and cumulative distribution function of Gumbel's distribution we have already discussed while discussing about different probability distributions coming under continuous random variable. Let us revisit into that again. The probability density function of Gumbel distribution is given by f of x is equal to alpha e to the power of minus alpha multiplied by x minus beta minus e to the power of minus alpha x minus beta. X is varying between minus infinity to plus infinity. The range of x's random variable is from minus infinity to plus infinity. The random variable can take the values between minus infinity and plus infinity. And coming to cumulative distribution function, cumulative distribution function is represented by capital F of x, that is given by e to the power of minus e to the power of minus alpha multiplied by x minus beta. Alpha is the scale parameter and it is greater than 0, and beta is the location parameter that can take values between minus infinity to plus infinity. The parameters of Gumbel distribution are described by alpha and beta. Alpha is the scale parameter and beta is the location parameter, that is, it is representing the central tendency. It is nothing but the mode of the distribution. Location parameter beta is representing the mode of the distribution. The same probability density function and cumulative distribution function I have repeated here because we need to write it in a simplified form. For that, what we are going to do, let y is equal to alpha multiplied by x minus beta. We are having a term alpha multiplied by x minus beta in this distribution. That is making the expression very lengthy. So, for that, what we are going to do, we are going to substitute alpha multiplied by x minus beta to be equal to y. This y is known as Gumbel's reduced variate, which is a dimensionless variable. So, this y is termed as Gumbel's reduced variate. Now, after substituting for alpha into x minus beta as y, the probability density function takes the form f of x is equal to alpha e to the power of minus y minus e to the power of minus y, and the cumulative distribution function capital F of x takes the form of e to the power of minus e to the power of minus y. So, here instead of x you can put f of y and capital F of y, because y we have written as a function of x, or simply you can put as small f of x and capital F of x, it does not matter. So, these are the expressions corresponding to PDF and CDF when we are substituted the Gumbel's reduced variate. So, here we have written cumulative distribution function in terms of Gumbel's reduced variate. We can write Gumbel's reduced variate in terms of CDF, that is in terms of capital F of x. How it will be? We can take the logarithm on both the sides of the equation, then we can find out the expression for y. So, y will be taking the form minus ln 1 by f of x. Gumbel's reduced variate y is equal to minus ln 1 by f of x, and cumulative distribution function f of x also we have written in terms of Gumbel's reduced variate. Y is related to cumulative distribution function. We know this cumulative distribution function can be related to the probability. What is cumulative distribution function actually? Cumulative distribution function is the function representing the relationship between the cumulative probability with the value corresponding to the random variable. So, what we are going to do? We are going to relate these Gumbel's reduced variate with the probability and the corresponding return period. That is, we want to write the expression for y in terms of return period t. So, Gumbel's reduced variate and return period can be related by making use of the basic fundamentals of probability. We already know that probability P, exceedance probability P given by Px greater than or equal to small x, and that can be written as 1 minus Px less than small x. By making use of the complementarity rule, we can write Px greater than or equal to small x as 1 minus Px less than small x. Now, Px less than small x, what is it? It is nothing but our cumulative distribution function, that is 1 minus capital F of x. Now, we will make use of the relationship between the return period and the exceedance probability, that is P is equal to 1 by t. This relationship we have already seen yesterday. So, P is given by 1 by t. So, we can write 1 by t is equal to 1 minus f of x. So, f of x can be written as 1 minus 1 by t, that is nothing but t minus 1 divided by t. Cumulative distribution function can be written in terms of return period like this, t minus 1 divided by capital T. Now, we can move on to the expression corresponding to Gumbel's reduced variate. Gumbel's reduced variate y is given by minus ln 1 by f of x. For this f of x, we will substitute the value in terms of return period. That will be taking the form minus ln 1 by t minus 1 by t, that is nothing but y is equal to minus ln t by t minus 1. This is the relationship with the return period. Gumbel's reduced variate is related to return period by means of this expression. So, if the return period is there, we can find out the Gumbel's reduced variate. Now, further moving on to the Gumbel's distribution, we will understand the parameters of the distribution. Parameters and various moments. Various moments means we know the expected value or the mean is given by the first moment with respect to origin, and the variance is given by the second moment with respect to mean. So, here let us look into the various parameters. Mean is given by expected value of x, that is represented by mu in the case of population. It is equal to beta plus 0.5772 divided by alpha. Beta and alpha we know, beta is the location parameter and alpha is the scale parameter. So, mean mu is given by beta plus 0.5772 divided by alpha. Beta is representing the mode of the distribution. And coming to variance, variance is the second moment with respect to mean. For the population, it is represented by sigma square. It is given by the expression pi square divided by 6 alpha square. Pi square by 6 we can calculate, that is coming out to be 1.645 divided by alpha square. So, here we are having the relationship with sigma square and alpha square. So, alpha can be written as alpha is equal to 1.28255 divided by sigma. Now we are having the value of alpha in terms of standard deviation. What is sigma? Sigma square is representing the variance and sigma is the standard deviation. We have written alpha in terms of standard deviation sigma. Now this alpha can be substituted in this expression for getting the value corresponding to beta. So here from this expression we can write beta is equal to mu minus 0.5772 divided by alpha. Alpha value we have already found out in terms of standard deviation, that we will substitute here and we can find out the value corresponding to beta. It is given by mu minus 0.45005 sigma. Now we have found out the expressions corresponding to parameters of this distribution. Alpha is 1.28255 sigma and beta is mu minus 0.45005 sigma. And these parameters we have discussed for the population. This is applicable to sample also. Gumbel suggested that when it comes to sample, the mean and standard deviation are functions of sample size. It depends on the sample size. It is not independent of the sample size when it comes to sample. So, sample case we are making use of the same expression, but notation is not mu, it is x bar. Mean is given by x bar is equal to beta plus 0.5772 divided by alpha, and from this beta can be written as x bar minus 0.5772 divided by alpha. And standard deviation is represented by S. S is equal to 1.28255 divided by alpha, and alpha is 1.28255 divided by S. So, this alpha can be substituted over here in the expression of beta. So, beta will be taking the form x bar minus 0.5772 divided by 1.28255 divided by S. So, it will be taking the form beta is equal to x bar minus 0.4501 S. So, we are having the expressions corresponding to alpha and beta in terms of standard deviation and mean. Beta is in terms of mean and standard deviation, alpha is in terms of standard deviation. So, if sample data is given to you, you can find out the mean and you can find out the standard deviation and you can find out the parameters alpha and beta. Once alpha and beta are obtained, you can substitute in the probability distribution functions and corresponding probability, return period and related to magnitude can be calculated. We know already we have how did we substitute? Initially the expression was lengthy and we have made it simple in terms of Gumbel's reduced variate. Gumbel's reduced variate y was nothing but alpha into x minus beta. Here we are having the expressions for alpha and beta. So, that we can substitute in this equation, then this expression changes into the form 1.28255 divided by S multiplied by x minus beta. Beta is x bar minus 0.4501 S. When we simplify this, it will be taking the form y is equal to 1.28255 divided by S x minus x bar plus 0.5772. This is the expression corresponding to reduced variate when we talk about the sample. I am simply giving the expression here. I am not going to give more conceptual understanding about these parameters, about this Gumbel's reduced variate. When you carry out further study, there are a lot of things to be understood. So, very minimal way I am coming over here. So, now we got the expression corresponding to Gumbel's reduced variate here in terms of sample mean and sample standard deviation. Now, for return period t, the corresponding magnitude of extreme event is x. So, magnitude of the extreme event is represented in terms of x and the corresponding return period is t. So, for this return period we can write this extreme event as xt and Gumbel's reduced variate by yt. So, the previous expression we are going to write as y of t and from that we will find out x of t. Y of t, instead of y we are just substituting yt. Yt is given by 1.28255 divided by S multiplied by xt minus x bar plus 0.5772, and from this we can get the value corresponding to x of t. Xt is represented by x bar plus yt minus 0.5772 divided by 1.28255 S. So, we are going to consider this particular term, that is substituted as k, that is xt is equal to x bar plus k is nothing but yt minus 0.5772 divided by 1.28255. This k is known as frequency factor. So, by making use of this technique, we can carry out the frequency analysis. In the previous lecture, we have discussed about frequency analysis by making use of probability plotting. We were arranging the given data in the descending order, providing certain rank, then finding out the probability and the corresponding return period. Based on that, we were able to find out the magnitude of an event corresponding to a particular return period. Here in this case, we are making use of this factor. Frequency analysis by making use of these type of techniques is termed as frequency factor method, and k is known as frequency factor. If you are making use of Gumbel's distribution for frequency analysis, the frequency factor is given by this expression k, and this is applicable to sample of infinite size, and frequency factor for different sample sizes and return periods are available in tables. Certain tables are given corresponding to frequency factor with certain sample data, not the data actually, it is the number of sample data and return period. Related to that, we are having the frequency factor. Any of the textbooks explaining this extreme value distribution type 1 Gumbel's distribution for frequency analysis, this table will be available there. So, this is something related to sample of infinite size. In practice, the samples cannot be of infinite size. This infinite size is not possible. We will be having a finite number of data in the sample. So, for finite size also frequency factor is provided. The expression is yt minus yn bar divided by Sn. Here the properties are related to sample, it is not related to infinite data set, it is not related to population, it is related to the sample data, that is yt minus yn bar divided by Sn. Yt is given by minus ln t by t minus 1, that is our reduced variate, and yn bar is nothing but our reduced mean, and Sn is the reduced standard deviation. Yt can be calculated corresponding to the return period. If you want to calculate it for 10-year return period, 50 years return period or 100 years return period, whatever be the value of t, we can calculate the corresponding reduced variate y, and yn bar and Sn can be obtained from the tables provided corresponding to reduced mean and standard deviation. Reduced mean and reduced standard deviation for different sample sizes are available in tables. Related to frequency analysis by means of Gumbel's method, when you refer in all the textbooks, these tables will be available. By referring to that table corresponding to particular sample size, we can get the value of reduced mean and reduced standard deviation. And the Gumbel's reduced variate can be calculated by knowing the return period. For different return periods, we can calculate the value corresponding to y. By making use of this method, if we are finding out the magnitude of a random variable which can occur for a return period of t years, that is not giving you the accurate value. It is depending on the sample size. As the sample size is changing, there is slight variation taking place in the magnitude of the event which is calculated by using this method. So, what we will be doing, instead of providing a single value, we will provide a range, so that the magnitude of this particular random variable can lie within that range, because certain uncertainty is involved with these variables. Such variables cannot be represented accurately by means of a single value. So, it is always better to provide a range, the value will be lying within that range. So, for that a new terminology is proposed, that is termed as confidence interval. The value of x of t, that is the value magnitude of the random variable corresponding to a return period t, calculated as mentioned before, may not be accurate because of the limited sample size. Always we won't be getting a very large number of data series. So, in such cases, if the limited data points are available, the x of t value, that is the value corresponding to the random variable for a particular return period, may not be giving you the accurate value. So, in such cases, instead of a single value, a range of values will be computed, that is termed as confidence interval or confidence limit. If you are carrying out the analysis by considering the variable as deterministic, exactly we can represent by means of a single value. But in the case of random variables, instead of a single value, we can represent the value of x of t within certain range x1 and x2. That interval is termed as confidence interval or confidence limit. It is the limits of the estimated value of x of t within which the actual value of x of t with a probability c will lie. The value of the random variable is related to a probability, right? So, that value can be within a range represented between x1 and x2, that is the confidence interval. So, x12, instead of giving a single value represented by xt, we can write x12 upper limit and lower limit we are specifying. Within that range, any value can be taken up by this x of t. So, x12 is given by x of t plus or minus f of c multiplied by sc. X of t is the estimated value of the variable with the given return period. X1 is the lower bound of the confidence interval and x2 is the upper bound of the confidence interval, and fc is related to the probabilistic function of confidence level and sc is the standard error. So, you just understand these parameters which are present in the expression for finding out the confidence interval, that is x12 is representing the lower bound and the upper bound. It is calculated based on the estimated value of x of t and the probability associated with the interval and the standard error. Standard error, there is different formula, and f of c is defined depending on the probability of the corresponding to the interval, and these things I am not going deep into the concepts. And as of now, for getting the flavor of this, I have put this because extreme value analysis, the magnitude we always put within certain confidence interval that can be calculated by using this function. Details related to FC, SC, all those things we can understand when we go a little bit advanced level, that is beyond the scope of this lecture. Now, let us go for solving some of the examples related to Gumbel's distribution, that is the extreme value type 1 distribution. First question is, in a river the annual maximum daily discharge follows Gumbel distribution with mean value of 10,000 meter cube per second and standard deviation of 3000 meter cube per second. Find out the probability that the annual maximum daily discharge will exceed 15,000 meter cube per second. Estimate the magnitude of annual maximum daily discharge with a return period of 100 years. We have been given the mean and standard deviation corresponding to the annual maximum discharge in a river. We need to calculate the probability that the annual maximum daily discharge will exceed 15,000 meter cube per second. That is the first part of the question. Second part of the question is to find out the magnitude of the annual maximum discharge corresponding to a return period of 100 years. Let us note down the data given. Those are the mean 10,000 meter cube per second, standard deviation 3000 meter cube per second. We need to find out Px greater than 15,000, probability that the annual maximum daily discharge will exceed 15,000, and second part is to determine the maximum daily discharge for a return period of t is equal to 100 years. By making use of these data, we can solve this example. We will start solving the example. The mean is given as 10,000 meter cube per second and standard deviation is 3000 meter cube per second. We know the parameters of the distribution. Mean is given by mu is equal to beta plus 0.5772 by alpha, and variance sigma square is given by 1.645 divided by alpha square. We are having the value corresponding to mean and standard deviation. So, we can find out the values corresponding to the parameters of the distribution alpha and beta. So, alpha is given by 1.28255 by sigma, because in the question itself it is given that it follows Gumbel's distribution. So, we can make use of the expressions which are provided for this distribution for calculating the parameters. So, alpha is equal to 1.28255 by sigma. Sigma we already know, that is 3000. So, alpha value will be coming out to be 4.2752 into 10 to the power of minus 4. Now, coming to beta, beta is given by mu minus 0.45005 sigma. Mean is 10,000. So, when we substitute mean and standard deviation in this expression, we can calculate the value corresponding to beta 8649.85. So, the parameters of the distribution are calculated now. Now, first part of the question is probability that the annual maximum daily discharge will exceed 15,000 meter cube per second. X of t greater than 15,000 meter cube per second. Corresponding to that, what is the exceedance probability? That is what we need to calculate. So, P is given by, small p is given by P of x greater than 15,000. From the law of complementarity, we can write it is equal to 1 minus P of x less than or equal to 15,000. So, P of x less than or equal to 15,000 is described by the cumulative distribution function. That is 1 minus f of x less than or equal to 15,000. We are having the expression corresponding to f of x less than or equal to 15,000. F of x is given by e to the power of minus e to the power of minus y. This is our cumulative distribution function in terms of Gumbel's reduced variate. Y is our Gumbel's reduced variate, and y is nothing but alpha multiplied by x minus beta. Alpha and beta we have already calculated. Alpha is equal to 4.2752 into 10 to the power of minus 4. Beta is equal to 8649.85. By substituting these values in the expression corresponding to y, y takes the form 4.2752 into 10 to the power minus 4 multiplied by x minus 8649.85. Now, we can substitute for x. Value of x is given to you. The annual maximum daily discharge will exceed 15,000. That is the value corresponding to x. So, x we can substitute as 15,000 and we can get the value of y as 2.715. Once the value of y is obtained, we can calculate f of x, because we are having the expression of f of x in terms of y. So, for y we will substitute in f of x, that is calculated as 0.9359, and capital F of x is calculated now. Now, we can calculate small p. Small p is given by 1 minus capital F of x less than or equal to 15,000, that is given by 1 minus 0.9359, it is equal to 0.064. The probability that the annual maximum discharge exceed 15,000 is given by 0.064. Now, we will move on to the second part. Second part is to determine the magnitude of the annual maximum daily discharge with a return period of 100 years. Return period is given to you 100 years. corresponding to that, what will be the magnitude of the annual maximum daily discharge. Now we will make use of the expression for probability and the relationship with return period. P is equal to 1 by T, our return period is 100 years. So, it is equal to 0.01. So, P is nothing but 1 minus capital F of x less than or equal to x, that is given by 0.01. We know the expression for CDF, cumulative distribution function, in terms of y, that is given by f of x equal to e to the power of minus e to the power of minus y. So, this thing we will substitute over here and find out the value of y. Once y is obtained, we can calculate the value of x, that is the magnitude of the maximum daily discharge. So, here in this y is alpha multiplied by x minus beta. So, alpha we have already calculated, beta also we have calculated. So, y takes the form given by this expression that we will substitute here in this equation for f of x, and we will substitute over here for small p, probability. So, by making use of this expression, we can calculate the value corresponding to the magnitude of the event x. So, this is 1 minus this particular term. So, this particular term will be equal to 1 minus 0.01, that will be taking the value of 0.99. Now, we are having the exponential function on the left hand side and we need to calculate the value corresponding to x. So, what we will be doing? We will be taking the natural logarithm of right hand side. Twice we have to do, e to the power of function is coming. Twice we have to find out the natural log of the right hand side, then we can get the value corresponding to this factor. 4.2752 into 10 to the power of minus 4 multiplied by x minus 8649.85 is equal to 4.6. From this, the value of x can be calculated as 19,409.92 meter cube per second. This is the magnitude of annual maximum daily discharge value for a return period of 100 years. So, this is the procedure which we need to make use while calculating the magnitude of the event, and also we have seen how to find out the probability related to the occurrence of a particular event by making use of the Gumbel's distribution. Now, one more example we will try to solve using Gumbel's distribution. The second example is given over here. Following results are obtained from frequency analysis using Gumbel's distribution. Frequency analysis is carried out for a river and the details which are obtained from that analysis is given to us. Return period and peak flow. Corresponding to a return period of 50 years, what is the peak flow? Corresponding to a return period of 100 years, what is the peak flow? These are given to us. And what we need to find out? We need to estimate the magnitude of flood with a return period of 150 years. Return period is given to you 150 years, that is the average recurrence interval for an event having a certain magnitude to be equaled or exceeded. For that return period, we need to find out the magnitude by making use of Gumbel's distribution. After carrying out the frequency analysis by making use of Gumbel's method, the results which are obtained is given to us, that is corresponding to return period 50 years and 100 years, what are the peak flows is already there with us. Now, we need to calculate the magnitude of the discharge corresponding to a return period of 150 years. We are having the expression related to the relationship between the reduced variate and the return period. It is given by y of t is equal to minus ln t divided by t minus 1. We are having the value of return period and corresponding peak discharge. So, y of 50 is given by 3.902. Here we are substituting t is equal to 50, t minus 1 49. So, we can calculate y of 50 as 3.902, and y of 100 also we can calculate in the similar way, that is coming out to be 4.6. And corresponding to 50 years and 100 year return periods, we have been given the peak value. We need to calculate the peak value corresponding to a return period of 150 years. So, corresponding to 150 years also we can calculate y150, that is coming out to be 5.0073, because by making use of this we are having the relationship of y and x. We want to find out the value corresponding to x. That is why we have found out the value of y150. So, we need to find out the magnitude of extreme event. We know the relationship with x and reduced variate y. Y is equal to alpha multiplied by x minus beta. Y50, Y100 and Y150 we have already calculated. So, from this we can write x is equal to y by alpha plus beta, that is x of t is equal to beta plus yt divided by alpha. X we have substituted as xt, t is the return period, and corresponding reduced variate y is y of t. So, xt is equal to beta plus yt divided by alpha, and we are having the values corresponding to x of 50 and x of 100. X of 50 is 42,000, that is equal to beta plus y50 by alpha. Y50 we have already calculated, that is 3.902. That we can substitute here. So, we got an equation here, equation 1. Now, corresponding to 100-year return period, x of 100 is given as 48,500 is equal to beta plus y100 by alpha. Y of 100 is 4.6, that we can substitute and we can get another equation given by 48,500 is equal to beta plus 4.6 divided by alpha. Let this equation be equation 2. These are two equations in two unknowns. We can solve in a very simple way, just subtract 1 from 2. Then we can get the value corresponding to 1 by alpha as 9312.32. Once 1 by alpha is obtained, we can substitute in any of these equations to get beta. Beta is coming out to be 5663.32. So, now we have found out the parameters related to the distribution. Alpha and beta are there with us, and y of 150, because we need to find out the magnitude of the event corresponding to a return period of 150 years. So, value of the reduced variate corresponding to a return period of 150 we have calculated. That value is 5.0073, and we are having the values of 1 by alpha and beta. So, we can proceed for calculating the value corresponding to x150. x150 is equal to beta plus y150 divided by alpha. We will just substitute the corresponding values and we can get the value of x150 to be 52,292.9 meter cube per second. So, this is the magnitude of the peak flow corresponding to a return period of 150 years. So, these are some of the examples related to Gumbel's distribution. So, here I am winding up the problem solving session on the extreme value analysis. So many examples and problems are there in these textbooks. Try to solve as much as possible number of problems. So, here I am winding up this session. Thank you.